Thank you, Brad. Next slide, please. Yeah, so we know I've heard a lot today, yesterday, the maps of minerals and many other things on the surface is critical for the Artemis exploration on the lunar surface. For example, we can help to prioritize the landing site. We can help to design the traverse for astronauts and rovers, and also we can provide a context for like return samples, and that can be very useful in future. So in this work, we explored the hyperspectral high-resolution imaging data on the moon that acquired by the Moon Mineralogy Mapper on board the Chandrayaan-1 mission. The lifetime of this mission is not very long. It's only like 9 months. It's from like end of 28 to end of 29. Next slide, please. Yeah, as some of you may not familiar with the MCube, it is imaging spectrometer measures visible to near infrared reflectance from the lunar surface. It's like the wavelength range is approximately from 0.4 to 3 micron. On the left figure, you can see how the instrument looks like, and on the right plot shows the spectral range of this spectrometer, and you can see it covers the major absorption features of the lunar surface materials, including water. I want to draw attention here are that there are 5 optical periods data, and 3 of them were acquired when the mission still had the star tracker, and also when the altitude was a little bit lower, like around 100 kilometer, so you can get a higher spatial resolution at 140 meter per pixel, and it covers around 60% of the whole data set. And another 40% of the data set has the best coverage. However, the mission loss is a star tracker, and also the mission altitude is a little bit higher at 280 meter per pixel. Next slide, please. Yeah, so here are the observation on the South Pole from 80 degree to 90 degree. Here's the pixel density. You can see on the left plot, left map shows the data with the star tracker. You can see it covers most of the Artemis zones, and you have at least like a few 10-ish to like few tens of observations at 140 meter per pixel. On the right map, I shows like stacked together with 140 and 280 meter per pixel. You can see covers essentially the whole polar region, and also you have more observations up to like over 100. Next slide, please. Then I use because we have so many repeated observations. I prepare like a high quality mosaic using pixels with the highest SNR, the signal to noise ratio, and also with the pixels with the star tracker are prioritized to use in the mosaic. And I can compare the mosaic with the loader data. What we can see on the red plot is there is a 2 small crater in the Stowe's crater wall. You can see it's like a kilometer, 2 kilometer size crater. It matches very well with the 140 meter per pixel mosaic with the like star tracker. Well, when I check the 280 meter per pixel like data, if there's no star tracker, you can see a little bit offside. But it tells you like we can use the data with a star tracker and get the best like registration for those pixels. Next slide. Yeah, so again, here's North Pole, similar story. Left plot showing data with star tracker, and the red one shows no star tracker. Combination of with and without star tracker. But anyway, in the polar region, you have like tens of repeat observations you can use to the mosaic. Next slide, please. Yeah, here's a map of the mosaic using the highest signal to noise ratio pixel, and also with the pixels with the star tracker. And also I check the registration of each pixel. Here I'm showing one example inside of the Rudolph-Swinsky K crater. You can see it's also like a kilometer size crater on the right side. The top one is Lola. The middle one is like a controlled mosaic, while the bottom one is just to use the data no star tracker. You can see the control mosaic, there is a great, especially great consistency with the Lola data. Next slide, please. Yeah, so then I can use the data to examine the mineralogy and the water at those Artemis landing zones. Here I only show two examples. So the first example is at the Nobile Rim region. And the first thing we notice is like there's a dichotomous distribution of hematite, the yellow pixels on the east-westing facing slopes. So the Noble crater wall face east, while the Stowe's crater wall faces west. And you can see the dichotomous distribution. The hypothesis is like the hematite was formed by oxygen from Earth's atmosphere, and the east-facing zones can capture the oxygen way easier than the west-facing. So that's why you see the dichotomous distribution. But this is again a hypothesis, so we need real data or like surface observation to examine this hypothesis. And another thing we notice like most of these mature regolith, so the greenish region is mostly regolith. And there is an interesting pyroxene exposure in the pink region circled by the pink circle. And here on the left, I shows the spectra of those different members, and including water. Next slide, please. Yeah, here's a water and ice map at this zone. This is a Nobile Rim. What we can see here is the water content varies dramatically. Like for example, pole-facing slopes, you can see easily like 300 above to like almost 1,000 ppm water, while on flat surface, what do you see is like relatively low, like 100 to 100 ppm. Uh, and we see higher water closer to PSR, but also the data is noisier. And there is also a small ice exposure we see here. Next slide, please. Here's another example. This is my favorite example at the connecting ridge extension and the Geologic rims. We can see again mostly is mature regolith and there's some like a hematite exposure on the ridge. It's very complex mineral composition at the Geologic rims. Here I'm showing one example. We see pixel size pyroxene ridge exposures near the like very small crater. This is like less than a kilometer, a few hundred meter crater. You can see the pixel size pyroxene, the pink one. And also you see some clusters of hematite exposures. And this is on the plot on the left showing the spectra of those individual members.
Minute 40.
Okay, great. Next slide, please. Yeah, this is the water at this zone. Again, it's highly variable across the whole region. It sounds like it's strongly affected by the topography. And we see more water on the pole-facing slopes, and also when it's closer to PSRs, for example, the Spudis and the Geologic. And the connecting ridge showing like around like 200, 500 ppm water. You have to zoom in a lot to see those like a brownish pixels. And the ridge extension shows like it's kind of a dichotomy. On the connecting ridge side is lower, but on the Geologic ridge side is higher. And the rims of Geologic crater is like relatively low, like few hundred ppm. And we see a lot of water ice exposures in the nearby PSRs. For example, the Spudis crater showing like high concentration of ice exposures. Next slide, please. Yeah, so this is a summary. We prepared thus far the best quality mosaic, well-controlled mosaic of MQ data in the polar region from 80 to 90 degree, and it has very good coverage for all Artemis landing zones at 140 meter per pixel, and we have water ice, and mineral maps at those from the data side, and will definitely help to solve a lot of science questions based on this data set, and including like a future Artemis exploration, like a surface ground observation and a sample returns. That's it. Thank you.